Let's have a look at our example with these measures. How can we calculate them? We see here in our example that the different occurrences directly translate into the sequence count. If, for instance, you look at the first sequence of activities where we have A, B, C, and D, and we know that this is occurring 12 times, this results in corresponding direct successor counts as you can read them here. Look at the activity sequence AB. We will find this in the first sequence 12 times, plus there's another one in the very last one, which goes A, B, C, E, and G, where this is occurring once. And this results in 13. This is the number of times that we observe the direct successor relationship A is being followed by B. So you can do this also for the other types of direct successor relationships that we have in our example. And this is then the basis to calculate the dependency measures. Most of them are easy to calculate since they are mostly one-directional. Let's stay with A and B. We see that A is directly followed by B with a dependency measure of 0.928. This 0.928 is the 13 divided by 14, since we do not have any counter directionality here. More interesting is how this dependency measure behaves when we have cases of concurrency. Concurrency from our examples is the relationship between B and C. We see that B being followed by C occurs 13 times. We also see that C is being followed by B, and this is occurring 87 times. If we now consider these measures, we need to calculate, for instance, for the case that C is being followed by B, 87 minus 13 subdivided by 87 plus 13 plus 1. And the number that we get from this is C being in the dependency relationship with B with 0.732. There's also the direction in the other way around, which is B being followed by C. This gives us minus 0.732, which is very interesting to note, since apparently this dependency measure ranges between -1 and +1. So in the case that we do not observe any relationship between the activities, it is 0. In case we have a direction on the one hand side, it gives a positive number, and if it is in the counter-directional side, we get a negative number. With these numbers that we have calculated here, we can now construct the so-called dependency graph. And you see in essence the structure that we have known from the process model in the first place. Each of the arcs in this dependency graph is being assigned with a number, that is the frequency of how often the relationship occurs, and the dependency measure, what we have just calculated, ranging between -1 and +1. This is the nice thing about the heuristic mining approach. Now that we have these different measures being associated with the arcs, we can use this for trimming down the graph and making it more compact and more abstract. One technique of doing this is that we try to filter based on certain thresholds. We can filter, for instance, on how often a certain relationship occurs. We can also filter on how often a certain dependency measurement threshold is being shown. And this is very helpful since it can make the model much more compact when it has actually been too complex in the first place. This is a very important advantage of the heuristic miner approach. And in this way, it helps to deal with noise in a way which the alpha algorithm is not able to provide. Therefore, it is very often used in practice because it provides a suitable way of abstracting. One final thing that needs to be considered when we apply the heuristic miner is that we also eventually want to construct a process model. The dependency graph does not directly show the process model, but it is a big step towards it. There are further heuristics, which we do not discuss here, that can be used for identifying whether certain points in the graph can be interpreted as an AND split or join or as an XOR split or join. Using such heuristics then provide the means to construct a BPMN model from the dependency graph.